And all of them that in the same rate. Oh, Ari. We got the pieces of it. Oh. Spreadsheets next. Which one are you doing? First plan was zip on.
6344.
Yeah, 63.417. That's in the negative project. 5,376.
That's a good one.
I got 5,000, so I had to check now. Capital H is within 6.7. Oh. Okay. So,
हेलो हाँ बताओ हाँ बताओ नेक्स्ट आपके काम बात आपके पास फोन में आपके इसलिए कोई प्रॉब्लम क्या है चलो मेरे नाम ठीक है क्या क्या 10005 तो कब से कब होना है मुझे शेयरिंग? ठीक ठीक ठीक। तो वो कुछ किया वो वाटर डे के बारे में? मैं क्या बताऊँ, आप भेजा है गूगल मैप में, वो भेजा है बना के नहीं व्हाट्सएप
So in this one, the problem, this was transmitted 1000, right?
Okay.
R is 5,
Right.
R is 5, R is 5. So K times H is very equal to 1000. Here also K times H is very much equal to 1000. Therefore, these two will be very similar. This one will be different because 1000 times 1000. So these two should be, so the first three should give practically equal answers. Because effectively the transmissivity for this is 1000.5, whereas this is 1000. Here, the transmissivity is 999. So all of these should basically do the same. This one will give you a slightly different value because the effective transmissivity is 1000 times, no, 100 times 1.1. So this is correct, right? So I'm getting different numbers. You can ask somebody else what they are.
They are getting the same values.
Yeah, the transmissivity effectively is not changing at all. Only the leaky aquifer it will be different. Because R changed.
7.3. So leak is 7.312.
What's that?
Leak 7.3.
Leaky aquifer how much? Shh. Do you want to see the answers for the others? Well, you need to get into spreadsheets. This is too much work, trying to do everything by hand.
No, sir, this I did long time back.
Which one are you looking at now? Oh, the leaky one was 7,300 something.
Yes. They give me 7,000 feet per size.
Okay. What was number 2?
So somehow I have missed it. This is like, not
3,
like
6, 12, 15, and 20. Yeah,
recently the third.
third one. Okay. How much did you get for pumping for each?
3,000.
3,734.
This process.
So for this one, I've done this one already. I want to do question number 2 and stop. Check the availability of pumping.
Then we will check this one.
I have done this one. I haven't checked anything. Actually, I haven't checked anything. So. But this one, after 12 hours pumping, you stop it.
Okay, so we have T minus.
Yeah. So basically, yeah, okay.
There is a recovery.
Yeah, I mean, we have the value some this one. Or this one. Very see if I enter the values correctly. Oh, wait a minute. Transmissivity in meters squared per day. Check the units. Just a second. Operating hours, speeds hours.
Six hours it is 2.8 seconds.
This time. Yes. What was that again? Where did we get everything?
2.8.
Just a minute. 2.87 part is correct.
That R
No. 2.87 are at the well itself. 0.5 meters.
point wise.
Just a minute. Just a minute. Something else here. Yeah, okay. What are the numbers you have?
12 hours.
At 12 hours at the pumping well?
At the well page is 3 meters.
In between, see.
At 100.97.
Yeah.
In 12.1 hours.
Uh-huh.
At the well page is 0.91 hours.
Yep.
Point 846.
Wait, at what time?
0.1 hours.
Getting a different value.
But 80 the
Worried, this is not used. I got at 100 meters at 12, I got 0.97. 12.1, I got 0.91. I got to check. I need to use it with my mobile. Before, at time 18, at the pumping well, initially it's 0.2, 0.21.
209.
Yeah, 0.209. Yeah. And at 24, it's 0.132.
0.13, yes, correct.
And then at 100 meters,
Almost came say 0.209 and for 18 hours.
yeah, 0.209 and 24 hours is 0.132.
Yes. Yeah.
So why is it off at 12.1? I got at 100, at 12 I got 0.979. But at 12.1 I'm only getting 0.916.
Well, they-
And what about when you put the image level? You do that one? Yeah. With the boundary, what did you get for the
T is equal to 6 hours.
time to equal to 6 hours? Yeah.
6 0.169.
The number of applications will be extremely long. Also the data.
Actually, the question entire I have kept it because here, if I didn't get the data for the
Wait a minute. You don't, I see, this is not even there.
it is not this.
Okay, all right. So this one, I have done it, but
Okay. I have
I
cut
have
off
to check. All
long
right.
time.
So you have to leave.
Correct.
Okay, all right. I'll at least tell them how to do it. I don't have the answers.
What I will do is I will do the scan of this.
That's fine. Yeah. But,
I will make
Hi. You are not able to stay for the tea break, huh?
not yes, yeah.
How is everybody doing? Does anybody have any questions on any of the first part? Very straightforward. What is the second part? We're still doing it.
Second answer
Oh yeah, which one?
from both except the third question.
Just a minute. Let me, the third question. This one.
Actually, I've done all of them except the third question of second part.
Oh, you did this one as well?
Yeah.
I'm still working on this. But this one you can't do because the data is not provided.
Okay.
But did you get this sheet? It might have been sent to you by WhatsApp.
Okay, then I will confirm the other question. Fourth part one.
For part one, we want to say
Last one.
the last one with the leaky aquifer is 7312.5.
Yeah, 17. 1.
And the others are 64.4. That's
Yeah.
Then which one?
The second question.
I haven't done this one. This is
Oh,
part
yeah.
two. I will finish part one, checked all the answers.
Yeah,
You're all correct.
I think so.
Okay, I've done part one. I haven't finished part two.
Then question number third.
Question number two or question number three?
Third.
Yeah, 371. That's 3734.73. Whatever.
37.
34.73,
Yeah,
which is very close.
You
Close.
basically did that.
Okay. And did you do this one also?
Yeah.
This one.
This is the answer of the question 2.
For question two.
That's the answer, and the question 3, this is the answer.
Consider the same, then you get. Okay, question number 3.
8.89, 9.24, 9.23, 9.57. That's it. The last two readings are not good.
12, 15, and 24.
9.7 and 9.94.
Yeah, with time, the drawdown should increase, right?
But we stopped the pumping at 12 hours.
Which one are you doing?
The second question, sir. These are the answers, I think.
Oh, wait a minute. So you're right. Oh. I thought I had done that, but maybe not. This is correct. Part 1. Oh, 12 hours. So, okay. All right. Okay. All right. Yeah, just a minute. Okay, let me finish it and I'll come back. But they did pumping stopped at 12, huh?
Yeah.
Missed that part. Which is
We check, I think, all the question.
for a period of 12 hours. Okay. I'll get back to you.
Actually, sir, I want to ask you one thing also. So I am confused with the TRR thing because when we take a 2D flow, we have both TXX and TYY, and we take it as a time field quantity, and we neglect we take XY is equal to 0 in this case. But when we take the same in the radial flow in all direction TRR, we take the same. So I'm a little bit confused that if we reduce the TRR from TX and Y or not.
Yes. So the title of my lecture is Engineer Bioremediation of Hydrocarbon Polluted Sites. So I'll be talking first about this bioremediation, that what is the technology of bioremediation, how we use the remedial techniques, and then particularly engineered bioremediation techniques to compensate or to increase the rate of bioremediation. We go for the enhanced bioremediation techniques. And particularly for the hydrocarbon pollutants. So if we look at these different types of the pollutants in groundwater, we categorize them in different categories based on the different aspects. So here I'm putting the list of the pollutants which are mostly found in groundwater, like volatile organic compounds, VOCs. These are the miscible type of contaminant which are going to be, you can say, not clearly mixed with the groundwater. And also they are volatile in nature, so they can also go into the soil here. Followed by the heavy metals, pathogens, nitrates, and pesticides originating from the agricultural activities. And then the salt and the emerging pollutants. And the last is the oxygen demanding gas. Generally, when it comes to the surface water sources, we talk about the oxygen demanding gas at the flow, and the other pollutants comes there. But since when these surface water infiltrate to the water zone, before it reaching to the groundwater, then all these organic demanding waste. So all these organic demanding waste are get filtered, and the possibility of getting these oxygen demanding waste are quite rare in groundwater. We can also categorize them based on the point of the diffuse source and the kind of the pollutant like miscible or immiscible. And also we can say that contaminant of the dissolution processes are not going to take place. Now the contaminant transport and the transfer mechanisms are, I'm very sure that you might have well described now in all the previous lectures. So when you talk about the pollutant transport into the subsurface, we talk about these three main mechanisms: advective, dispersive, and diffusive transport. Okay. So advective transport depend on the kind of the groundwater velocity. If the groundwater velocity is going to be high, we can say okay, advective flow is going to be more dominant. And then dispersive, mechanical dispersion is because of the presence of you can say the soil particles, where these because of velocity variation and also because of the touches both path these molecules are following. So the contaminant flume is going to disperse along the flow directions and also it transfers to the flow direction. That is the mechanical dispersion. Molecular diffusion is taking place because of the concentration gradient difference. So let's say at some place the contaminants leave and they move towards the surrounding location from the high concentration gradient low concentration. So combining these advective, dispersive, and diffusive transport are mainly going to govern the contaminant transportation. At the same time, the mass can also transfer from one form to another form. Maybe contaminants are there in the soil water, so they can be get absorbed or dissolved by these soil particles. That is going to be in solid form. They can at the same time there can be dissolution as well as the volatilization if their VOCs are there, and the decay or the attachment or detachment of the microbes or the pathogens which are there in the soil water system. Now, once our groundwater is contaminated, then the question comes that what are the different, you can say, the remedial technique which can be used for removing these contaminants from the subsurface. Now, we can categorize these remedial techniques like based on ex situ and in situ, based on the place where we apply those ones. We will talk about these technologies based on physical, chemical, and biological process. So in physical process, we remove the contaminants in a very aggressive manner if the contaminated site is very limited. Okay, and we are well characterized. In that case, we can use these aggressive techniques like physical based techniques to remove the concentration of the or the pollutant from the ground. But in these physical techniques, mainly the pure phase of the contaminants are removed. If the wide applicability of the or widespread of the pollutants are there in the groundwater, then it is not going to be so environmentally benign as well as the cost effective. Chemical techniques, we use the certain, you can say the chemicals or the other materials to react with the contaminants which are there in the subsurface. And that combining the physical chemical technologies, we again apply to removal of the contaminants, or maybe to convert these contaminants from the daughter product, from the original, you can say the product to the byproducts, which are going to be harmful or less harmful as compared to the pollutants. Now, the physical and chemical techniques are conventional techniques. Indeed, we can apply for removal of the pollutant, but their, you can say, environmental impact as well as the cost is going to be very high. In that case, the alternative techniques are going to be in form of the biological remedies. When we talk about the biological remediation, we talk about the like bioremediation or especially biostimulation, phytoremediation or bioaugmentation techniques. So this lecture is mainly going to cover this biological treatment of the groundwater sites. Now first we go for the bioremediation. Let us see what is bioremediation. So bioremediation is made of two words, bio plus remediation. So to remediate a polluted site using the biological activity, the biological power of the soil water system. So this is a grouping of the technology that uses the natural microbiota to degrade or transform these contaminants which are located in the soil system to less of the non-toxic bioproducts. So pollutants are there and we are using the microorganisms present in the soil water system, groundwater system to convert them into a less or the non-toxic bioproducts. Now question comes that what are the microbiota? Microbiota are, these are the microorganisms. Indeed, we cannot see from our naked eye. So they can be like bacteria, fungi, and the yeast. Out of these, bacteria are the most numerous one. So you can say the role of the bacteria is going to be more, you can say, prominent when it comes for the bioorganisms. And therefore, I am not going to use these other terms now. So far, the bacteria or the microorganisms are going to be used as a synonym for my form. Now, in bioremediation technique, we talk about, okay, this is environmental benign, very cost effective. You can apply at a larger scale without having any side effects of this technology. But the efficiency of this bioremediation technology is quite low. It means the time needed for the remediation of the pollutants using the bioremediation technique is going to be very large. Sometimes it may be 100 years or 100 plus years, depending on the site condition, depending on the level of the contaminants. Now, question comes that, okay, how to accelerate this remediation technique, bioremediation, using some interventions, using some engineered techniques. Therefore, we categorize this bioremediation technology into engineered bioremediation technique like biostimulation, bioaugmentation, plant enhanced bioremediation, or you can say simply phytoremediation. So, what we do in biostimulation? In biostimulation, the environmental conditions are provided in the favorable, you can say, the zone of the microorganisms, the field. And also the supplements, so the nutrients, you can say, are also provided so that the bacteria can work more efficiently, their metabolic access can be increased. The example is like that, if the temperature of this lecture is fairly good, then you can concentrate more on your lecture. If you are taking your lunch or dinner, so you can also do your work more efficiently. Similarly, the microorganisms are also needed the favorable environmental conditions as well as the nutrients for their metabolic actions. So in biostimulation, we provide the supplements and also the favorable or the optimal environmental conditions to increase the metabolic access of the bacteria or the microorganisms. If they are working more efficiently, indeed the time needed for the bioremediation is going to be less. Second technology is the bioaugmentation, in which what we do, we generally develop the new strengths of the microorganisms, or in the simple words, we go into the lab, we go to the market, buy the microorganisms, and go to a polluted site and insert those bacteria additional bacteria to that site. So already there are bacteria available at the polluted site, and we also introduce the new strain. So the number of the bacteria which are going to be responsible for degrade these contaminants are going to increase. If the number of the bacteria is going to be more, so indeed the time needed for removal of the contaminants is going to be less. Now question comes that, okay, which technology is going to be superior in our Indian condition, for instance? Some people say, okay, biostimulation is more effective as compared to the biomedication, and others also, they claim that, okay, biomedication is going to be more effective. Similarly, some suitable plant species are also used to increase the, you can say, rate of bioremediation. So plants can play, many roles in increasing the rate of the bioremediation. Not only the biologically, but also the physical removal of the contaminants can also take place because of this presence of the plants. So to check these different, you can say, the engineered bioremediation techniques, we have done some experiments, practical experiments. Before I mention those practical experiments, I am showing this bioremediation technique that is the base on the plants. So in general, we say bioremediation is a technology where we use the microorganisms. If we go more specifically, like when you use some plant species, then we call it phytoremediation. And then further, this phytoremediation technique can be categorized like phytoextraction, rhizodegradation, phytostabilization, phytodegradation, phytovolatilization. So based on the kind of the contaminants which are there in subsurface, and based on our objective, whether we are to completely remove the contaminants or we want to degrade those contaminants into the subsurface, so we can use any of these technologies as per our, you can say, the need. Now, what happens when you provide the plants? Let's say this is a Meadows zone. I'm not talking about the groundwater for the time being. This is the Meadows zone. This was polluted earlier by some pollutant. Okay. Before these plants are provided, there was contaminant. Now, after plantation of these specific, you can say that by these plants here, the contaminants are taken up by the root biomass, plant root biomass, and then subsequently these contaminants are translocated from the root biomass to the above ground part that is known as shoot biomass. So pollutants are physically removed because water uptake by plants is taking place. So indeed, contaminants which are dissolved in the water, they are also taken up along with the water by the roots. So contaminants are physically removed. And also the microbial activity in this root zone is going to be much intense as compared to unplanted or the barren sites. So whenever you go to, let's say, barren site, which is not having any plant, you collect a soil sample or water sample and maybe a sample from a planted site. You will see a lot of microorganisms in the planted site as compared to the unplanted site. So the number of the microbes are also going to be more in the rhizospheric zone. We call it rhizospheric zone. And also the contaminants are physically removed by the presence of these plants. That is how, and also it is the plant roots also releases some, you can see the carbon source, and also the oxygen availability is also better. So indeed, oxygen is one of the electron acceptors. So microorganisms are going to work more efficiently in presence of the electron acceptors like oxygen and the other carbon sources. Now to check these sites, bioaugmentation, biostimulation, and phytoremediation, I am providing one, you can say that this case example of L-Nepal polluted site. L-Nepal here stands for the light non-aqueous phase liquids. So non-aqueous phase means these are immiscible type of the food, like all the hydrocarbon, or you can say that the petrochemical industry which are having all the products. Like you will go to the gasoline station, you will see the petrol grade of different types of the chain of the hydrocarbons. So if you put this hydrocarbon oil along with the water, they are not going to mix freely. It is going to remain in a separate phase. But a small portion of this hydrocarbon oil also mixed with the dissolved with the water, and that is good enough to degrade the quality of the groundwater. So they are immiscible in nature. If their density is lighter to the water, we call it light non-aqueous phase liquids. Or if they are denser to water, we call it DNAPL. All the chlorinated hydrocarbons comes under the category of the DNAPL. And the light non-aqueous phase liquids are mostly the monoaromatic hydrocarbon like BTEX compound, toluene. One of the, you can say, very popular, you can say this solvent in the industry. If you go to any industry, the toluene is used as a solvent, very popular one. So these monoaromatic hydrocarbons are going to come under the category of the LNFR, and the rest of the like dry cleaning industry we use the PCB or TC trichloromethane. So all these chlorinated hydrocarbons are coming under the category of the DNAPLs. DNAPLs are generally they are more carcinogenic in nature as compared to the LNFL, and degradation of the LNFLs in aerobic conditions is quite fast as compared to the DNAPLs. Now, if you look at, there are two pictures of this slide here. One is on the left hand side. This is for LNF. Now, you can see this is a gasoline station here. You go to any petrol pump, you go to Roorkee, you will see many this gasoline station. So, all these stations are having a storage tanks like that, which are not visible indeed at the surface, but all these pumps are going to have some for containing these hydrocarbon oils. Now, initially, these storage tanks are made free from the leak, but later on, with progression of the time, by degradation of the material by which this sump is made of, or maybe by some technology, sometimes we take it, sometimes we don't. Okay. There is some sort of the leakage which takes place. The leakage can be very minute, can be quite significant as well, but believe me, most of these gasoline stations are having such type of the leak issues, and detection of these leaks are very good. Not only in India, anywhere in the world. Now, what would happen if there is some leak of the hydrocarbon which is taking place from a pipeline or from such type of the storage tanks, which is there below the surface? So, the hydrocarbon oil is going to start moving to this Weddell zone. And what the driving force for the movement here? Gravitational force. Because in Weddell zone, when there is a leak is going to take place, so it is going to move vertically because of the gravitational force. And during its movement, you can see this red color is the pure phase of the hydrocarbon oil. And then there is a yellow zone, and this is the contaminated soil area. Okay. So this is because volatile in nature, so this is going to also pollute the soil area surrounding to this trajectory. And if sufficient leak is taking place from the source, this hydrocarbon oil will meet to the groundwater table. And after reaching to this capillary range here, the hydrocarbon oil is going to retain over this water. It will swim as a pancake over the top of the groundwater table rather than going into deeper levels because its density is lower. Now, when it is a film of this LNFL is retained over the groundwater table in small zone here, then a small fraction of this LNFL is also get dissolved with the water that is going to create a contaminated film of the ground. Maybe few ml, few liters. And that is going to be a longer source for the contaminating the groundwater. So whenever somebody is extracting the groundwater from the down gradient side or even from the up gradient side of this leak, opposite to the direction of the groundwater flow. So here the groundwater is flowing from the left to right. Contaminants can also travel in the opposite direction because of the molecular diffusion. So when somebody is going to take out the groundwater here, so we can see not only the groundwater but also the soil air which is coming from this polluted zone that is also containing the traces of this pollutant. Now, Heathrow Airport in the world, one of the best examples for such type of that. So there are many, refilling of this aircraft are taking place. So a layer of the LNFL is there below the airport. You go to any airport, not only the Heathrow Airport, but any airport or any gasoline station, such type of the situation can near to this our upper Ganga Canal in Roorkee. So you can see a petrol pump there. So that is also going to have such type of the sump, and the samples have been found to contain such type of the traces of the hydrocarbon oils. Now, if it is a DNAPL, if the density is higher than the water, then instead of retaining this DNAPL over the groundwater table, these DNAPLs keep traveling into the saturated zone as well, unless they find some maybe a temporary impervious barrier, or they will reside in the hard zones, which is going to be quite deeper, and they can stay happy for longer time. That's a thousands of years. Why I'm saying here longer time? Because oxygen is deficient. This is saturated zone, and the degradation of these DNAPLs in this saturated zone here is going to be very slow. Okay. And this is not only the source of the contaminant, but also the path through which these contaminants are moved from the source to the variably saturated zone. That is also going to be a source of the pollutant, because a fraction of these hydrocarbon oils is also retained by the soil micropores while they are moving through the variably saturated. Now the LNFLs, they remain mostly into the near to the groundwater table, But groundwater table is also not a static phenomenon. It is keep changing, like say seasonally, yearly, or maybe sometime diagonally it can go to the coastal region. So because of this dynamics of the groundwater table, their spread area is also going to be quite large. So a small spread, a small leak of the hydrocarbon oil of light nature can also affect the larger area. But the oxygen is little bit available, you can say, through this bedrock zone, and that is why the degradation is going to be faster than the dynamics. Now, to check this bioremediation technology for such type of the polluted site, we have done very simple experiment in the lab. When I say simple experiment, microcosm experiment to the column experiment. Okay. Initially, we check the impact of the temperature. Because if you go to like India, country like India, if you go to north or the south, there is a huge difference in the temperature. Or not only from the location, but temporarily also, like if you go out from the home state of Rajasthan, in winter time the temperature goes very low, let's say 1 or 2 degrees, but during the daytime the temperature rises very high. Similarly, in the summertime, you can see temperature can be more than 45 degrees Celsius. So temperature variation of the sites are quite significant in our country. To check this impact of the temperature on bioremediation technologies, we assembled these microcosm experiments, batch experiments, completely mixed systems. We have taken 3 temperatures, T1, T2, and T3. T1 represents a low temperature, like let's say winter scenario. T2 is a room temperature, representing our autumn or maybe spring season. And then T3 is high, representing the summer season. So 30 degrees Celsius, we kept 21 degrees Celsius room temperature, and this was kept around 10 degrees Celsius, at 10 degrees Celsius. So we wanted to check that how the temperature is going to impact the removal or the remediation of these contaminants by the bacteria. Now there are, you can see on the left hand side, 3 diagrams are there. These are at constant temperature. Okay. Now you can also argument here that okay, why only the constant temperature? Because temperature is also very dynamic. Daytime temperature becomes high and nighttime the temperature gets very low. So in that case, we also kept these batches alternatively at low and high temperature. Let's say 12 hours for the low temperature, and then they are moved to the 12 hours for the higher temperature. So that is how we mimic this for the diurnal fluctuation of the temperature, and by keeping them at constant temperature, we represented it for the seasonal variation of the temperature. Now this figure, these 3 figures are showing the constant temperature when we kept these one at 10 degree room temperature and at high degree T3 temperature. The solid line shows the sterilized batches. Sterilized means the microorganisms were killed, controlled. There is no presence of the microorganism. So you can see the concentration of the toluene, which is relative concentration C upon C naught on the y-axis, and the time of progression is on x-axis in hours. So the time, with the time you can see the almost the concentration of the toluene in these batches remains similar, because there were no micro, they were completely closed, so toluene could not escape from the microcosm. The dot shows the live batches, where you can say the time required for removal of this toluene took around 100 hours. Now when the temperature was rise from 10 degree to 21 degrees Celsius, the time needed for the removal of the toluene was around, let's say, 40 hours. And then when we further increase it to 30 degrees Celsius, there only 20 hours of the time was needed for removal of the toluene by the bacteria. So it was concluded that okay, for every increase in, let's say, 10 degrees Celsius temperature or so, the time, the degradation rate of the microorganisms was increased twofold, or the time required was half of that. Okay? And this is for fluctuating temperature. You can see the controls are also fluctuating here. That is because of the Henry's coefficient. When you rise the temperature, you can say the fraction of the contaminant also goes to the air phase. So that shows this fluctuation in the sterilized batches because of the temperature variation. And here you can say the time needed is going to be, when we shifted them 10 to 21 degrees Celsius, it was 60 hours, more than little bit 40 hours, and then you can see here again 50 plus minutes. What we concluded from this fluctuating temperature, so if we provide lot of temperature variations to these bacteria, in that case, these bacteria microorganisms, they don't like such type of the pressure. The temperature stress is going to be more. So if we can keep the temperature of the polluted site somehow at a constant rate, then the impact of, or you can say the rate of bioremediation, or the bioremediation is going to be a little more effective. Also, if we can keep the temperature higher means it is not like bacteria will, the rate of bioremediation will keep increasing the temperature. There is an optimal range, and we found that the temperature of around, let's say, 30 to 38 degrees Celsius is good enough for the mediation of, is the, you can say, the most optimal temperature for the mediation of the toluene. Similarly, you can target any other contaminant, there may be some optimal temperature for that particular contaminant. So the temperature, if we can keep in an optimal range of the particular bacteria which is responsible for degrading that contaminant at the site, that can increase the rate of bioremediation. That can increase the efficiency of the bioremediation. Now, if you assume that okay, natural polluted sites cannot put an umbrella and can keep control the temperature, it is going to be the natural phenomenon. Indeed, but we can always customize the land use and land cover by providing, maybe by maintaining optimal soil moisture conditions, by plantation of the site, or you can say by providing maybe heated water, wastewater using the west. So those are the, you can say, interventions which can be taken at the site to increase the rate of bioremediation of a polluted site. Later on, we also see the impact of the moisture content for the removal of the contaminant from the rural zone. So integrated impact of the temperature and the moisture content of the soil was investigated. We know that the bacteria are also very, they are live entities and they need moisture, they need oxygen both. So there is always an optimal range of the oxygen as well as the water content where the rate of their metabolic action is going to be most efficient. Now, we have investigated this technology in this IIT Roorkee campus, this bioremediation technology. What we have done, we have taken a sample from an industry. I'm not going to name the name of the industry here. This is the petrochemical industry. Sorry, this is the petrochemical industry, and we collected the polluted groundwater from surrounding petrochemical industry. So shallow tube wells were there, hand pumps in there, and we collected the polluted groundwater from that site. So contaminated water, groundwater was collected from this site, and we are having bhavans here. The wastewater is generated from these bhavans, hostels. The primary treated wastewater is also collected from the campus. Now, idea of collecting this wastewater is to have the nutrients in this waste resource. We calling it the waste resources, but that is also going to be used for the biostimulation. And the polluted groundwater is coming from that side. We designed 4 sets of the microcosm experiment. The first one is the natural bioremediation. We have not done anything. We simply kept this contaminated groundwater in this microcosm at room temperature. Second case, we mix this wastewater with the polluted groundwater in 1:1 ratio. 50% was groundwater, 50% was wastewater. Any doubt? So 50-50. The idea of mixing this wastewater with the groundwater was to provide a lot of nutrients to the bacteria which are there in this polluted groundwater. It's just like you can say this is a case of bioaccumulation. In third case, we pass this wastewater through a wetland, a small constructed wetland in laboratory scale, and the water was passed through by maintaining some time of residence here, and then again this has been mixed with the contaminated groundwater to see the role of the plant, to see the role of the vegetation over bioremediation. And then final case, similar to the third case, the only difference is here, we also polluted this wetland with the hydrocarbon. Why we polluted that one? Because there are 2 ways. Either you go to the lab and take this bacteria and provide on the site. The second one is naturally we can also develop these bacteria strands. So if you provide some contaminant in the soil, after some time, maybe after 10 days or 15 days, if you go, you can see the respective bacteria which are going to eat those bacteria, these contaminants. So bacteria are also generated naturally for targeting those contaminants. So idea of contaminating this wetland is to develop bacteria which are responsible for eating this hydrocarbon oil here. So that was a toluene here in that case. All these 4 cases we analyzed in the laboratory, and what we saw that there was no difference in the time of degradation of the contaminant in case 1 and case 2. The hypothesis was that in the second case that if we mix the contaminated groundwater with the nutrient water here, we are going to provide supplement. Yeah, like all these major in the micronutrients are supposed to be there in the wastewater. But the biostimulation was not successful in that case. The time needed for case 1 and case 2 was almost similar. There was no significant difference between case 1 and case 2. So first one is the natural, you can say the biodegradation. The second one is the biostimulation. We try to spike these contaminated groundwater with the nutrients which is coming from this treated wastewater. So what could be the reason, in your opinion, that this technology was not successful? Do you understand that one? The difference between 1 and 2. The first one was merely groundwater, which was containing this pollutant. The second case, nutrients were supplied to this wastewater. Biostimulation case. So when you go for the biostimulation, indeed we are supposed to give that lesser time for the bacteria to degrade that, because bacteria are going to provide it with the supplements. Yes? You follow me?
Need more than nutrients.
More than?
More than just nutrients.
Yes. So whatever the groundwater we collected from here, that was already full of the nutrients. So this is a very intense agricultural activity area surrounding the lagoon. So farmers are using a lot of NPK fertilizers here. And later on, when we analyze this groundwater, we found all these nutrients in this groundwater as well. So it's just like that, you are taking your lunch and you are offered one more plate. You will say, no, I am okay now. So similarly, the microorganisms also, they are also living entity. So they were already having these nutrients, and when you provided them extra nutrients, that is not going to have impact on the their metabolic base. But in third and the fourth case, we found that some encouraging results because of the presence of the plants, and the time for degradation of the contaminant was quite less as compared to this first and second case. So the learning from these simple experiments was that before we go for the implementation of any remedial technique in the field, you have to understand the field conditions followed. You have to characterize the site very well. Okay. And that's the reason that we learned from that, and then we investigated the polluted site here. You can see using all these sample soil and groundwater sample collection, as well as the geophysical and other analytical techniques we use for characterizing the entire body saturated zone, including the groundwater and the polluted surface water body in that area. Now, thereafter doing these experiments, we have also conducted some continuous experiments using the vertical column experiments, where the contaminants move through the very saturated zone. And then we integrated these column experiments with the wetland to just see the impact of the wetter zone of the plants. So contaminant when released at the surface or below the surface, they started moving through this unsaturated zone, and then the fate and transport mechanisms can be, you can say, investigated by collecting the sample, periodic sample, and by preparing these breakthrough curves from this the concentration of the pollutant which we obtain from the different depths of the soil. These are the some observed and as well as the simulated results, and further we have upscaled it for the 3-dimensional time scale experiments, where the groundwater table was also kept dynamically moving. So we changed the flow of the groundwater. We also keep changing the groundwater table location as well to see the dynamics of impact of the groundwater table dynamics, as well as the impact of the groundwater flow velocity on the fate and transport of these hydrocarbon oils to this in subsurface. So yeah, those are the some, you can say, the findings. I will not go in much detail here. So you can see here. So these are the release point of the pollutants at time t equal to 0 under, let's say, the slow groundwater velocity, you can say the moderate groundwater velocity, and this is going to the faster groundwater velocity. So we kept moving the groundwater from the right to left side, you can see here. So after this release of the hydrocarbon oils, they started moving into Vadose zone here. You can see the movement of this Vadose in the Vadose zone. And after reaching to the groundwater table, they started spreading predominantly in the direction of the groundwater flow. So this is under, you can see the lower groundwater velocity, this is moderate, and this is going to be the further faster. Now that was the one case example, but before the target and remediation technique, monitoring technique is also very crucial. So how do we go for that? Let's say government of India says Indian river is polluted, and then DSP along with other international agencies are giving a lot of you can say spending a lot of fund on investigation of the contaminants in the Indian basin. There are many more 4 states in India where the polluted sites have been identified. So what we do generally, we generally take the actions when the entire ecosystem or when they started having their impact or the population which is dying in that area. That is the stage we generally go for the remedial or you can say the managing the activity. Before that, whenever the contaminants are released, let us say that this is the release of the contaminants. And after some time, after few days or few hours or few weeks or few months, they started impacting the local flora and fauna. Maybe the most sensitive species of the plants are affected after few weeks. And later on, this impact is going to be to more other species, and then it is going to have the entire ecosystem of the tree. So if we can identify the pollution episode, the contaminated site well before it is going to have the impact on the entire ecosystem, we can apply this early intervention. We can save a lot of cost for the remediation of these polluted sites. Okay. So for doing that one, we propose this physico-chemical technology along with this biomonitoring. Biomonitoring, there are many bio indicators in the field. They can give a very crucial information of the contamination, even like level of the contamination sometimes. So conventionally, we do generally we identify the site, we go there, collect the samples, we analyze the samples in situ sometimes, or maybe using some advanced equipment in the laboratory, and we go for this physico-chemical analysis for most of this monitoring time. But biomonitoring technique is ignored during this site characterization. So if we can integrate this biomonitoring, indeed, physical chemical technique, they have their own advantage. So along with these physical chemical techniques, we can, somehow we can save our ecosystem. We can also apply these remedial techniques more effectively and more timely. Now this is the last example where I'm showing the application of this phytoremediation technique in the field. How many of you have visited Madsa and Vrindavan? Or at least some of them. So Madsa and Vrindavan, this area is known for the node, you can see the Baldam node in the stem. There are a lot of water bodies, small ponds, talab, were there in the past. And the name of these water bodies are kept like Brahma Kund, Baldam Kund, Radha Kund. All the kunds, the water bodies are named with God and goddess. Now this is the condition. In the recent past, we visited along with one NGO. So most of the water bodies, most of these talab, most of these water kunds are like. So because groundwater table has gone down, this comes under arid and semi-arid conditions, so evaporation losses are quite high. And then some constructions you can say near to these water bodies, and this stress material is also you can say dumped in those water bodies. So the Dredge Foundation, along with our technical guidance, they revived these water bodies, and I'm showing the example of Brahma pond here. So Lord Brahma is sitting here in the middle. A nice this pond was all this stress material and everything was removed, and then nice construction you can see here using this red stone. And local plants were also, these plants not for the beautification, but the idea was to provide these plants, and these plants are interacting with the water which is filled in this pond. Okay. So idea was to make use of these plants for the water quality improvement of these ponds. because it's not flowing water, it's stagnant water almost. Groundwater table is deeper. So, but plants are not magicist. You cannot say that everything can do the plant, one or two plants can do. No. As compared to this volume of the water, the plants were not sufficient to improve the water quality. So there are two issues faced by these, you can say the local people who are maintaining those homes. The first one was related to the water quantity. Water quantity, because this water table is gone down, so we suggested them to fill those water bodies from the tube well using the groundwater sources of the nearby area. And then during the summertime, after 7 days or 6 days, the entire water was disappearing because of the higher evaporation loss and also some seepages with the deep percolation. The second issue was related to the water quality. So water started smelling bad after some time because again it was stagnant water. The first issue for the evaporation loss, especially because mostly the water was evaporated. So we suggested them, because we know already, you might have also read this during a BTech, that there are different physical, chemical, techniques which can be used for checking of this excessive evaporation losses. You cannot put again a barrier or umbrella over the top because it's a large one. So in that case, we suggested them to use this hexadecanal type of this chemical. We generally make a very thin layer of the water molecule, and that doesn't allow much water molecules to go into the atmosphere. So somehow 30 to 40% of the, you can say, the evaporation loss was controlled by using this technique. The second issue was related to the water quality, and that was quite unsuccessful because initially we suggested them to use these plants, and the plants could not improve the water quality. Then later on, we suggested them to use the sprinkler. Sprinkler now you can see here, so it was installed later on. So idea of putting this sprinkler not for only aesthetically, but was supposed to increase the dissolved oxygen. But then when they started operating this sprinkler, the oxygen was dissolved, pure level was increased, but at the same time operation loss was high. So we suggested them to operate this during the early morning or maybe late evening, some hours only, not continuously. So that is how at some extent the water quality was improved. And the other example I say you, that if you go to Gujarat, like Sabarmati Canal, I don't know whether you've seen or not, the entire canal is covered by the solar panel. Right? You need a lot of space for installation of these solar panels. Sometimes many industries they are using the large agricultural area to install their power plants. But this canal, which is having a lot of space over the top, was used for installation of the solar panels. At the same time, it was used to check the excessive evaporation losses which are taking place from the canal. And the electricity now is supplied to the area of the villages through which this canal is passing on. And the same technology has been followed by many Europeans now. It's not like us, we are copying our technology from the others, but if your mindset is positive, let us say, oh, India में कुछ नहीं हो सकता, सब कुछ contaminated है, सब कुछ polluted. No, it's not like that. If you have polluted your site, if you have contaminated your groundwater, if you have contaminated your soil water sources, we also have the power to remediate. We also have the skills to manage our natural resources. So it is a way of thinking that, especially for you investors, that if you can think positively, if you can think critically, indeed things are possible, and we can manage our water sources more effectively. So with these words, I would like to thank you for your sincere listening, and would love to have the questions related to what I have presented.
We will discuss about hydrogen. So suppose we take the example of nitrate contaminant. So there nitrogen is possible going.
Right.
So how to remediate that? Whether by using this nitrification technique, whether you have that plant will kill the bacteria which cause the nitrification denitrification, or how
The plant will not kill these all the pseudomonas of the bacteria which are toxic. They will not kill that one. But of course, phytomedicine technology is not going to be directly applied to the polluted groundwater. You have to use your groundwater which can be pumped, it can be passed to the well also. Okay, for the irrigation. If the nitrogen level is high, we know that most of these CGW report you might have seen that every district of the country is very high level of the nitrogen. So you can analyze, one can analyze that what is the level of the nitrogen, and the farmers they can be they can be given the guidelines for using this nitrogen because already nitrogen is there in the water, groundwater. Sometimes that you might have seen in Rajasthan when there is rain or when they are using the groundwater, the crop productivity is different, completely changed. So that is because of the availability of the nutrients which is there in the subsurface. So that is what I am talking about, that characterization of the water resource, whatever the water you are using, is very important. Based on that one, decisions can be taken. And nitrogen removal, yeah, of course, it is going to be larger extent. But then, yeah, at least we can judiciously apply the fertigation at right time and right place to further can save the shallow groundwater resources, or the underlying groundwater resources for becoming more nitrogen rich. Yeah.
So then enhanced bioimitation, we have to term bioaugmentation. And that process we, in a way, we are applying external artificial bioorganism, we are adding it to the ground so that we can faster the rate of the
Absolutely.
the process of contamination.
Yeah.
So as it's an external process, or we can say it's an artificial process, so is there any negative effect of it on the ground?
Mostly bioaugmentation, when we apply the threshold time, the starting of the degradation, that is also important. As soon as you introduce the new strain of the bacteria to the site, they will not start working. They need some acclimatization time. So that is why you might have observed in my graph, I don't know whether you've seen it or not. So there's a yes. You see there is a straight line here. Can you see the straight line?
Yes.
Yes. This portion here. There's no degradation, right? So this is the time of acclimatization. So depending on the site conditions, sometimes let's say you apply this bacteria at very older stages in Jammu and Kashmir. Temperature may be very low there. So this time of acclimatization may be very large. And there are other geochemical reactions, or you can see the pollutants or the nutrients which are there at the site. They are also going to determine the effectiveness of the fate of these microorganisms which are there. So we have to indeed, doing this simple experiment, one need to check the effectiveness of bioaugmentation or biostimulation before you go for the real application of that. You can see the technology.
Sir?
Yeah.
After this topic, we had topic temperature and limitation, and there was a third point written no limitation of water.
No limitation of water means?
So it was written in the first.
Okay. This one?
Yes, sir.
Back. Okay.
Third point, no limitation of water.
Oh, no limit. Okay. So these were saturated. Okay. This was saturated case because it was this, you can say over-saturated case. So soil and the water are mixed in the batches. But this is representing the degradation of the contaminant in equipment. And the next case which we have seen, there is impact of moisture content is what for gravel soil, where we took the unsaturated soil with different soil moisture content. I didn't describe that. So water was not limiting there because bacteria need both water as well as the, you can say, the oxygen. So there is a must be limit ratio of the oxygen and water that is going to be most, you can see, the favorable condition for effectiveness of the method.
Can you put that? Yes.
Sure.
Sir, these methods which we have discussed, like phytomediation and other techniques, like it is only applicable to lab experiments or on field also can be applied.
Of course, the ultimate idea is to apply in the field. What we will do in just investigating the laboratory. So controlled conditions experiment becomes very, not only the experiment but also modeling. I didn't mention anything on the modeling. So performing the modeling exercise and the practical experiments, controlled experiments are very important before you do real field application or you go for the field application of this technology. So modeling aspect, I'm very sure Professor Goenka is covering those one, but those are also very important. So you want to check that okay, how much time this bioremediation or fire remediation technology is going to take to reduce the level of contamination from C1 to C2. What you will do? Either you wait in the field or you do some simulation experiment and find out okay, it is taking 8 years. You can take your decisions before you go for the field. So the role of these practical experiments and the numerical experiments are there to reduce or to apply these technologies more effectively.
But it seems difficult, sir, in field situation because in lab everything is controlled, but in field it is not enough control.
That is why I'm saying. See, I told you the temperature you cannot control. Fine. I give the example in Jeddah, in Saudi Arabia, there is a polluted site, not groundwater, but general polluted site from the hydrocarbons. Downstream of the law of science and technology, they gave some project. So the site was heavily polluted by this hydrocarbon, not only N-methyl, D-methyl and N-methyl, cocktail of the contaminant of hydrocarbons. But it was very dry. So what we suggested, whatever the water which is coming from the data front, we told them that use this wet water to maybe just irrigate that. So moisture level can be increased. So for the very dry soil, if you look at the degradation of the pollutant, that is going to be slow as compared to the moisture level that's near to field capacity, where the water is also there for the microorganisms, oxygen is also there. So if we can maintain those favorable conditions for the microorganisms, of course, you can increase. If you can increase the rate of biomodulation by delta, it's worth it knows. Or maybe if the site is there, that is barren site, you will suggest to use some specific plants which can target those contaminants. They can physically remove and also they can create those contaminants. That can also be applicable. We are applying this in Gajrola, in UP, where a lot of groundwater is polluted by coloration for sugar industries. Okay. So those. See, if you think that okay, you cannot do anything in the field, then you cannot do anything. I agree that there are a lot of difference doing the experiment in the lab and applying this lab experiment transferring to the field. But why we are doing that one? We want to first check that okay, these are the conditions of the field. You do those simple experiments before you go for the field. If you don't do this, if you don't characterize the field, in that case, certainly there's a high possibility of failure of these technologies.
Any question? Thank you.
After the